So we're going to talk about radical expressions this period. Let's just talk about product property of radicals. All right, the first one, we're going to start off rather simple. You have square root of 4, right? And that is what? 2. Well, why is it 2? Because it's in here, it's 2 times 2 in the square root, right? And what is the square root 2? It groups numbers by 2's, right? So every time you can get a pair, they come out as a single 2. That's why this is a 2. All right, well, what about 8? How much is that? 2 radical 2. Again, because 8 is made up of 3 2's, you group them by 2's, right? One comes out and one stays in. So let's do a little exploration here, right? So why don't I write root 8? Now I know it's 2 times 2 times 2. Can I write it though as 2 cubed? Is that the same as the square root of 8?
Yeah.
Yes, right? Now, what is the index for the square root? 2. Right? Now, so what if here, remember how yesterday we were dividing the power by the index, right? So what if we did the same thing here? Divide by 2, divide by 2. So what would we get? 3 divided by 2? It's 1 and a remainder of 1, right? It's 1. 3 divided by 2 is 1 with a remainder of 1. So what happens? You have 2 to the power of 1 because 3 divided by 2 is 1. And then how much do you have inside? 2 to the power of 1. So basically each of those ones, right? When you divide 3 by 2, you get 1 with a remainder of 1. All right? So that's another way that we can do it. So what if you didn't have the square root of 8? What if you had the square root of 32 then? How much is that? It's the square root of 2 to the power of what? 5, right? So now, if this is 2, and if we divided this by 2, okay? 5 divided by 2 is what? 5 divided by 2 is 3.5. It's 2, remainder 1. 5 divided by 2 is 2, remainder 1. So it'll be 2 to the 2, and inside 2 to the 1. Okay? Because 5 divided by 2 is 2, remainder 1. Okay, so it would be 4 root 2. Yes?
Could we just do it the way, like...
You could do it the way you were doing it before.
Okay.
Yes, I'm doing this mainly because of, for the variables.
Okay.
Okay, so look at this next one. X to the power of 5 in a square root, right? The index is 2, so I'm going to divide by 2, right? So 5 divided by 2 is what? 5 divided by 2 is 2. So I have x squared outside, and what stays? X. Okay? Let's take a closer look and let's see what really is happening. We had x to the power of 5. Is that x to the power of 5? Yes. And I'm going to group them by 2's because it's a square root, right? So 2 x's come out for an x square, and 1 stays in. You see how you get the exact same thing? So you can do it any which way you want, okay? Now, what about this next one? Now what are we going to divide the 7 by? 3. So 7 divided by 3, how much is that? 2 with a remainder of 1, right? So it's d squared cube root d. All right? 7 divided by 3, I get 2, remainder 1. Okay? All right, here I have 12c to the 6 d cubed. All right, so what is the 12? It's 4 times 3, which is 2 times 2. So how much is it? 2 root 3. So 2 outside, 3 stays inside. Now, what's my index? 2. So I'm going to divide 6 by 2, and it'll be c cubed, no remainder, so nothing stays inside. And the other one is d cubed, which I divide by 2. So how many comes out? d to the power of 2,
1.
d to the power of 1, and 1d stays. Okay, yes.
Would you put the C in absolute value?
Oh my gosh, yes you would. Yes, you would. Okay, the C, how do we get the C? It's an even root, even power, odd exponent. So it's in absolute values. Huh? 3D. For part F, we have the cube root of 27, right? So cube root 27, how much will that be? 3. Now, for the y, I'm going to divide by 3. So I will have 1 remainder 1. So 1y comes out. 1y will stay. Yes. Wait a minute. Let's do the z as well. So z, 7 divided by 3. That's 2 remainder what? 1. So 2 will come out and 1 will stay. In the case of quotients, if you have the square root, the nth root of a over b, right? The nth root of a over b, you can split them up so you have the square root, the nth root of a over the nth root of b. So you could split up the fraction. In fact, if the roots like this are split up, we combine them, and if they're combined, we separate them. All right? So, all right, so take a look at part A here. We're going to separate this. So it's going to be the square root of y to the 8 over the square root of 9x. Okay? So what am I going to get here? Y to the 4th, because it's y to the 4th over 3 radical x. But you can't, right?
You have to multiply both sides by radical x.
Okay. Brownie points for that. Brownie points for telling me what the name of that process is.
Multiplying the bottom stuff
The denominator.
It starts with an R.
Rationalize the denominator.
Oh, rationalizing the denominator. Rationalizing the denominator. There we go. Okay. So, putting the two together from Ethan and Brandon, we now have to rationalize the denominator. Why rationalize? Because a square root that won't go away is an irrational number, right? So we have to make it rational. We have to rationalize the denominator. Multiply by root x, top and bottom. So this is going to be y to the 4 square root of x over 3. Now when you have root x, it's just x. Okay, let's do the next one. Cube root of 2 over cube root of 9x. Okay, now, in the top, I can't do more with this. But in the bottom, I don't want to leave a root there. All right? So what I have to do is I have to complete the roots. Now, if it's a cube root, in order for numbers to come out of there, you need a total of how many of each? 3 of each. So let's just rewrite this for a minute. Let's rewrite this. This is cube root of 2. And in the bottom, I have cube root of, now what's 9 in terms of its simplest base? What power is it? It's 3 to the power of 2. And I have an x in there. Now, I need a total of 3 of each of the elements in the denominator. So hang on, I'm doing this, and then I'll take questions. I need a total of 3 3s, and I need a total of 3 x's. That means I have to add in some additional ones to complete this. How many more 3's do I need to add in? 1. And how many more x's do I need to add in? 2. So now I'm going to multiply this by the cube root of just 1 3, because along with the red ones, now I have 3 3's, which is how much I need. And I'm missing an additional 2 x's, so I'm going to put that in here. And you must do it to the top if you want to be consistent, mathematically accurate. So let's see what we have here. In the numerator, I have the cube root of, I multiply everything, so 6x squared. And in the denominator, I have the cube root of 3 cubed, which is just 3, and the cube root of x cubed, which is just x. Okay? And that's how you leave it. You cannot simplify the 6 with the 3, right? Because one is inside a root and one is outside. All right, we're taking things up a notch. I have a 5 outside. I'm going to multiply these two. And then in the cube root, if I multiply everything, I have 1,000 and a cubed, right? So that's 5 times. Now, what's the cube root of 1,000? 10. And what's the cube root of a cubed? 8. So this is 58. All right. Okay, here. All right, now look, for ones like this, there are several ways to do it. You could simplify each radical potentially on its own. Or you could just combine and do it. Let's just combine and do it. So the outside numbers multiply together, right? So I think of roots as, a number in a root is, think of it as somebody in jail, right? And if a number is not in a root, then they're not in jail. And you know that normally people in a jail don't normally associate with people outside. So you can't multiply one from the outside with one from the inside. You can't divide one from the outside with one from the inside. Okay? So 6 times 4 is 24. And in the square root, I have 8 times 2, 16. And how many C's? And how many D's? 8. Right? So then finally, it's 24 times 4. How many C's come out? C squared, and how many D's? D to the 4. So 24 times 4, 96 C squared D to the 4. Okay, question. No. Okay. All right, so here. All right, to add roots, you can add only when you have identical roots. So only when roots are identical. So for example, if you have root 3 and root 3, or root 7 and root 7, okay? So that means I need to simplify each one of these. So here I have 4, and what's the root 8? What does that simplify to? 2 root 2 plus 3, and now you need to simplify the 50, right? 50 is 2 times 25, so it's 5 root 2. Now, combining the first, you have 8 root 2 and 15 root 2. So we're going to add the coefficients, 23 root 2. So again, you have to simplify to get to the same root. Now, let's say you simplify and it turns out that you don't get the same roots. Then you just leave it that way, but simplify. Okay? All right, so let's do that next one. You have 3 times root 45, which is what? 3 root 5 minus 5 times what's 80? So it's 4 root 5 plus 4 times what's 20? 2 root 5. So I have 9 root 5 minus 20 root 5 and another 8 root 5. 9 plus 8 is 17 minus 20. Negative 3 root 5. Okay. All right, the next, I believe there are parentheses here, right?
Yeah.
Okay, so we're going to distribute. More and more, I want to get away from the term FOIL, right? Because FOIL is it's sort of like a mnemonic that we use. But once you get away from binomials, like if you're multiplying 3 times with 3 terms, right? 3 terms and 3 terms, there is no more first, outer, inner, last. So I want to, rather than FOIL, I do want to use the correct mathematical term from now on. The distribution, right? This is the distributive property. You distribute the 2 root 3 to everyone, and then you distribute the 3 root 5 to everybody. So, distributing the 2 root 3 to everybody in the second parenthesis, I get 6 root 3, and then I have 2 root 3 times negative root 3. That's negative 2 times what? 3. Then the 3 root 5, distribute to the 3, I get 9 root 5. Then distribute to the negative root 3, so it's negative 3 root 15. Okay? So let's see. Is there anything to simplify here? Not really. So let's just let's just put it all together. And there's really no order, but convention is to write the one without a root separately. You can either put it all the way in the front or all the way in the back. I'm just going to put it all the way in the back because there is a minus, and we don't like dangling minuses anywhere. So 6 root 3 plus 9 root 5 minus 3 root 15 minus 6. Sometimes you will have like terms, sometimes you will not. All right. This next one, any patterns? A minus B, A plus B. So what am I going to do? Square the first one, right? Square the first one. What does that give you? 49 times 2. Square the last one. What symbol, what sign in the middle? A negative. So this is 98 minus 27, 71. All right. For this one, again, it's the rationalization. What we need to multiply by, remember we used the complex conjugates? Well, these two have conjugates, but they're just conjugates in this case. So multiply by the conjugate. Okay? So this one, I'm going to multiply by root 6 plus 5. Just switch that second number. All right. In the numerator, I will have 8 root 6 plus 40. In the denominator, I'm going to have the square of the first minus the square of the second, right? In this case, there is no I, so it remains a minus. So root 6 squared is 6 minus 25. So this is 8 root 6 plus 40 over how much? 19. Negative 19. That's the final answer. Or we can write it negative 8 root 6 minus 40 over 19. Now this second version is more conventional. That's probably how you'll see it in the back of the book as well. All right. Now I'm going to leave the last one for you guys. I'm going to give you guys 5 minutes to do this next one. You're going to multiply by the conjugate. It's going to be a little bit more complex, but I'll give you 3 to 5 minutes. Okay, so this is what I have, right? So just this one thing. So here we got 10 root 3 minus 27 over negative 13. The negative then, right, gets distributed there. And this is a totally perfectly way of writing it. Most of the time, however, we do switch it to this form, okay, because again, it's just so much cleaner to have that negative inside as opposed to the first term of the problem, right? So that's that one.